Hi, in this video, I'm going to present Ivy, which is a framework that produces instrumental variables for causal inference. To give an overview of our work, we first would like to talk about causal inference, which is the study of understanding causal relationships. We then talk about how we might use instrumental variables to understand causal relationships and the practical challenges associated with it. Finally, we will talk about how Ivy might be helpful to alleviate some of these practical challenges. Let's get started. To illustrate the process of understanding causal relationships, let's consider whether smoking can cause heart attacks as an example. We want to show why understanding these causal relationships is challenging. Here, smoking is the risk factor, and heart attack is the outcome. Although smoking has a positive observational correlation with heart attack, that does not necessarily mean smoking is the cause of heart attack. For example, high stress level can cause a person to smoke more and more likely to get a heart attack as well, making smoking and heart attack positively correlated with each other. Here, stress level is called a confounder, and these confounders, especially when they are unobserved, make causal inference particularly challenging. To avoid the influence of these confounders, one can run randomized control experiments, or RCEs, in order to study causal relationships. In our example, an RCE random splits the population into a control group and an exposure group. People in the control group are forbidden to smoke while people in the exposure group are forced to smoke. We then can compare the heart attack occurrence rates between the two groups to draw a causal conclusion. What is the issue with RCEs? Well, in our case, it is extremely unethical to run such an experiment. One way to avoid doing such an experiment is to use an instrumental variable. Instrumental variables are variables from observational data that behave like an experiment. It is independent of the confounder and influences the outcome only through the risk factor. In our case, cigarette price can be treated as an instrumental variable because it is independent of confounders such as the stress level of a person, and it only influences heart attack rate by changing the smoking rate. However, in practice, nearly perfect IVs like cigarette price are difficult to find. Instead, we sometimes have access to many imperfect IV candidates. For example, genetic variations that predict nicotine addiction can be IV candidates for smoking and heart attack. These IV candidates are imperfect because they might be weak IVs, dependent on each other, and they might not even be valid IVs altogether. Failure in accounting for these imperfections will lead to unreliable causal estimates. To deal with imperfect IV candidates, we propose Ivy. Here is an example. We wish to use a high-quality IV Z to infer the causal relationship between X and Y, but such a Z is unobserved. Instead, we observe some IV candidates that are valid, but they are potentially weak IVs in green associated with Z. Meanwhile, we also observe some IV candidates that are invalid IVs in yellow. For example, W4 is invalid because it is associated with the confounder. We now describe how Ivy operates. In step 1, Ivy identifies the subset of valid IVs among the candidates. Meanwhile, Ivy also estimates the dependency between the valid IV W2 and W3. In step 2, we use the valid IVs and their dependencies to synthesize the IV of better quality, Z. Finally, we use the synthesized IV Z to estimate the causal relationship between the risk factor and the outcome. We validate our method through theory and experiments. Theoretically, we provide sample complexity results for the estimation error of our method. We characterize how dependencies and the number of invalid IVs among IV candidates may influence this error, and how this error translates to the performance of downstream causal effect estimators, such as the commonly used Ward estimator. Empirically, we show that IV may deliver less biased causal estimates on various real-world datasets. This is indicated by a median effect size that is closer to the ground truth, which is 0 in our case. We have described IV, an algorithmic framework that aims to synthesize IVs of better quality from a set of imperfect IV candidates. You are welcome to find out more about our method, its applicability, and limitation from our paper. Thank you.